In this video, we are going to review linear systems, and by choosing the best method to solve this linear system, either by graphing, elimination, or substitution. A quick review. A system of equations is two or more equations in the same variable, which means two or more lines. A solution to a system is a point or points that will satisfy each equation in that system. Let's take a look so we remember what it is in a system to have one solution. With one solution, if we have two equations or two lines and we are to draw them, a point will be our solution. I've drawn an example of two lines on this coordinate grid, and you'll notice that right here there is the point of intersection where the two lines cross, and that would be the solution to the system. This particular point would be a solution to both of the linear equations. In the next example, if I were to draw two lines that have no solution, that means that these lines would not intersect, and therefore they would be parallel, so there would be no solution. In the next example, if we were to have two lines in our system, and they would be exactly the same line when we drew them, they would have infinite solutions. So again, one solution, no solution, and infinite solutions. There are three methods for solving. The first is our graphing, and it's easiest to graph when our equations are in the slope-intercept form. So you want to ask yourself, is it in y equals mx plus b? The second method is substitution, and when we are substituting into another equation, you will want one variable by itself or isolated. The third method, called elimination, or sometimes called linear combination, we want the variables to be lined up into standard form. We'll take a look at reviewing these three methods. The first method that we're going to take a look at is solving by substitution. Notice that we have one equation that is solved for one variable, and it doesn't matter which variable it's solved for, but in this case it's in slope-intercept form. So y is equal to this quantity. What we're going to do then is to substitute that particular expression into the other equation, taking out the y and putting the new information in its place. So I have x, and then I put in the new expression, which is x plus 5. I substitute that for y, and then I have equals 1. Our goal is to have an equation in one variable to solve. So when I combine like terms, x plus x is 2x, and then I will subtract 5 from both sides, and I have a simple equation to solve, which is 2x is equal to negative 4. And when I divide by 2, x is equal to negative 2. We are looking for the intersection, the point on the coordinate plane that satisfies both equations. So we do need to take the x equal to 2 and substitute that into one of the equations to find the y coordinate of that particular point. It doesn't matter which one we use, but we do want to make life a little easier. So if you take the negative 2 and replace it into the top equation, all I have to do is a simple math problem. Negative 2 plus 5 is equal, negative 2 plus 5 is equal to 3. So the point on the coordinate plane that is the intersection of these two lines is the point negative 2, positive 3. I can check that solution also into the other equation and make sure it is correct. Negative 2 plus 3 is equal to 1. That is our point of intersection, which is the solution to the system, and it works in both equations. In the next example, we're going to work on solving by elimination. The first thing we need to do is to make sure that our variables are lined up, x's, y's, equal sign, and our numbers or constant is on the other side. If you recall, the second step is to make sure that one of the variables is the exact opposite of the other. To do that, we must multiply one, the other, or both equations by a value that will then have one of the variables be opposite. We could do either the x's or the y's. In this case, since the top equation has a 2y, I could make the bottom equation be negative 2y if I multiply the entire equation by negative 2. When I do that, I will have, by distributing, positive 6x minus 2y is equal to 4. I'll simply rewrite my top equation on top of that, and then I will add the two equations together. The goal again is to have one equation as the result, which is in one variable. Negative 5x plus 6x is 1x, 2y and a negative 2y is 0, and 14 plus 4 is 18. Now I have the x coordinate of the point of intersection, so I need to substitute that 18 for x into either of the equations. I'm just going to do the top equation, so I have negative 5 times 18 plus 2y is equal to 14. Negative 5 times 18 is negative 90. So to finish solving, I'm going to add 90 to both sides. 2y is equal to 104, and I'll divide both sides by 2 to finish solving, which results in y being equal to 52. So my point of intersection is at the coordinates 18, 52, and that is the solution to my system, which is the point of intersection. To be sure, I can substitute the 18 into the second equation, which gives me negative 54 plus, substituting y, 52. Negative 54 plus 52 is equal to negative 2, and therefore it is a solution to both of my equations and a solution to the system. The next method is to solve by graphing to find our point of intersection. So I'll take my first equation, y equals negative 2x plus 7, recalling that my y-intercept is 0, 7, and my slope is negative 2. So when I graph, I will put my first point at 0, 7, and find other coordinates by using my slope from that point. Down 2 over 1, down 2 over 1. I draw in my line, and then I should label that line accordingly. This line is y equals negative 2x plus 7. In the next example, I have y equals 4x minus 5. My y-intercept is at 0, negative 5, and my slope is at positive 4. So I will put the point on the coordinate grid at 0, negative 5. My slope is up 4 and over 1, up 4 and over 1. I'll draw my line, and then I will label my line with its equation, which is y equals 4x minus 5. And I can see on the graph that my point of intersection is at the point positive 2, positive 3. I can again check this algebraically by substituting the point 2, 3 into both equations, and that should be correct. Here are a couple of more examples. If we take a look at the first one, we can see that it is set up so that y equals negative 3x plus 5, where this equation is solved for the variable y. Because it is set up so easily for substitution, I'm going to take this quantity and I'm going to replace the y in the second equation with that expression. So I have 6x plus 2, and I'm going to put parentheses around my expression, negative 3x plus 5, as I substitute in, equals 1. Now I'm going to distribute, and I'm going to take the 2 times the negative 3x and the 2 times the 5. Negative 6x plus 10 is equal to 1. To finish solving, I want to combine like terms. 6x minus 6x is 0. So my result is 10 is equal to 1. This situation where the variable drops out, where we have a number value equal to another that is not true, would give me an answer of no solution. These two lines, if drawn on the coordinate plane, because there is no solution, would be parallel. Parallel lines have no solution. In the next example, you'll notice that the variables are lined up in the correct order. I will use elimination for this solving. To do that, I want one of the variables to be the opposite. So I already have a 12x in my second equation. How can I make this x be opposite? I can multiply 4x by negative 3, and they will be exact opposites of one another. So when I distribute, and please remember you must distribute the negative 3 to all the terms in the equation, I have negative 12x minus 15y equals negative 36. And I will rewrite my bottom equation directly underneath. I will add the two equations together. 12x and a negative 12x is 0. Negative 15y and a positive 15y is 0. And negative 36 plus 36 is 0. The variables have canceled, leaving us with the situation 0 equals 0. This is a true situation, and therefore if we were to draw this on the coordinate plane, these would be two lines directly on top of one another, and therefore we have infinite solutions. So let's review. You are finding the point of intersection of two lines. There can be one solution, infinite solutions, or no solution. With one solution, we are coming up with two lines that have one point of intersection. With no solution, we have parallel lines, and with infinite solutions, we have two lines directly on top of one another, or being the same line. Here are some final hints. When you are solving by graphing, it's a good idea that you avoid fractions, because if the point of intersection is not crossing at a corner or at integers, you will need to estimate and won't get the exact answer. We also avoid decimals and large numbers. We would like to be as close to the origin as possible. For substitution, one of the equations must have a variable by itself, a variable that is isolated. And for elimination, we want to make sure that the equations line up. Then we need to multiply one or both equations to get one variable to be the opposite. Then we add together and finish solving. Please remember to complete the reflection.